No, 3 and 4 are infinitely different from each other. Okay, so I've got an applied force of 3 newtons, and because of constant V, that means my force of friction must then also be 3. Newtons, newtons, newtons. Cool. So then the last piece of this, what is the coefficient of friction? Well, we've got 2 expressions for the force of friction. One is that the force of friction is equal to 3. And the other thing we have here is that force of friction is equal to mu Fn. So mu Fn equals 3. So mu times 20 equals 3. So mu is going to equal 3 over 20, which is something small, I'm willing to bet. 0.15. What was your question, just for out of curiosity's sake? Well, you actually told us how the force of friction equals 3, Jasmine. You're the one who said, because there's F net equals 0, that means F net has to equal FA, and FA is 3. So I can take this a step back. No, you're good. That's 4. Angelina, cool? What was the one tiny detail that derailed the whole thing for you? Okay, so this step here. Okay. Good carrot. Number 6. Eric, what was your question? Also 6. Okay, let's do 6. A 6.2 kilogram object pulled along the horizontal surface by a force of 22 newtons. It is accelerated 1.1 meters per second. Or if it's accelerated, what is the coefficient of friction between the 2 surfaces? Cool. So let's draw the thing. I've got my object being dragged along a surface. FG is going to equal 6.2 times 9.8. So in this case, they've given us the mass. It's level, and there's nothing acting up or down. So Fn is going to equal Fg, which is going to equal what? 60.82? Okay. I'm going to go with the majority here, 60.82. 60.82. Okay, so there's my Fg and my Fn. We're told that the applied force is being pulled by a force of 22 newtons. And we're asked to find the coefficient of friction, so there must be a force of friction, and it must be going which way? The opposite, and I'll call this Fa, the opposite of the applied force, so let's label it in there. That's my force of friction. And I'm looking for the coefficient of friction, so I'm going to punch in right here what my FF is equal to. Force of friction is equal to mu Fn. That's all we know at this point. So now we're told this thing is accelerating. We've got an acceleration of 1.1 meters per second squared, which means we have to start. We have to start from here, because there is an acceleration, we're not going to have things nicely balance each other. So I've got F net equals ma, now I can start sliding things in here. What forces are acting in the plane of motion for this object? Force applied and force of friction. Which one of they're acting in opposite directions, so what direction do you want to call positive? Doesn't matter. Which one do you want positive? Luis wants to the left positive. Jasmine wants to the right positive. For the sake of this question, that's fine. Yeah. So for the sake of this, because we're told that it's accelerating, this value here is positive, we can assume that this thing's accelerating because of the force that's being applied here. So I'm going to, just for the sake of keeping things nice, I'm going to call it to the right positive, but you don't have to. You can go the other way, and it would just give you a negative value. The acceleration would then be negative, and they would cancel out, leaving you with a positive mu. So the sum F net is the sum of the forces. So what forces are acting? You said Fa and Ff. We said to the right was positive. So what's my expression here now for F net?
equals to 6.2 times 1.1.
Okay, that is the next line. Jasmine gave us the previous line. Now Luis just gave us the next line. 22 minus, and the force of friction is mu Fn, so it's going to be mu times 60.82 equals 6.2 times 1.1. And now we solve. How do I want to do this? I'm going to add this expression over. I'm going to subtract this expression over, and then I'm going to divide by 60.82. So it's going to give me 22 minus 6.2 times 1.1, all divided by 60.82. Yes, that's Winston. Equals mu. Yes, you're not hallucinating. There is a dog next door. His name is Winston. He's adorable. So your value for mu, that's the expression. 0.249? Perfect. And then the answer key says it's 0.25, so that rounds nicely. That is question 6. So it involves everything we've done. Who said that? Yeah, sure, Tangent. It involves everything we've done up to this point. Questions, comments, concerns. Where are things fuzzy?
Oh, no, I got the right answer. I just did it a different way. I'm not quite sure how I did.
I'm like 90% sure you didn't do it in a different way, but you think you did, but you didn't.
No, I totally got a different value on the denominator. I got 58.8.
Okay, then there were mistakes. Mistakes were made.
Okay. Well, I got the right answer.
Well, you couldn't have.
Well, I
If
did.
your values were different, you can't get exactly the same answer if you put a different value down
It
here.
was different too. I didn't do time
Well,
1.1.
Okay, so you made multiple mistakes along the way. They cancel each other out. Fantastic. Those are the worst kinds of scenarios. Because like I did it right. No, but no, you did everything wrong in the perfect way. Because if you didn't multiply by the acceleration, then if the acceleration doesn't show up anywhere,
No, the acceleration did show up.
well, either you did it the way I did it, or you made multiple mistakes that canceled each other out. Because the way Jasmine and Luis laid it out is the way to do it. While Connor's trying to figure his life out, we're going to do number 7, because that was the next one someone asked about. A 1,250 kilogram car traveling at 60 kilometers per hour comes to a sudden stop in 35 meters. What is the coefficient of friction acting on the brakes? So we're going to assume here that this is a rolling stop,
Man, it's good.
not a sliding stop, because we're told what we want to find the coefficient of friction acting on the brakes. So there's my car. Rolling on the ground. FG's down, FN's up because it's level. FG is going to be 1250 times 9.8. That's going to be something. That better not be negative.
I would agree.
That sounds more reasonable. You probably gave us a final answer there, Cohen. Something like that. So I've got Fn and I've got Fg. What other forces are acting on this car? Friction from the brakes, and that's going to be going which way? To the left. Force of friction is mu Fn. We don't go on coefficient of friction, do we? We do want the coefficient of friction. Okay. The coefficient of friction is mu Fn. Is that it? Must be. So this is going to be which direction do you want to call positive? We're going to the right is positive, okay. So then let's plug this thing into F net equals ma. Everything we do in this chapter starts here. So then what is the sum of my forces acting in the direction of motion? What forces are acting in the direction of motion? Friction's the only one. We said to the right was positive. Friction is acting to the left. So what am I going to put here for F net? It's not just the force of friction. We said to the right was positive and the friction's acting to the left. So this is going to be negative force of friction equals 1250 times A. Now, we have to go through and find A, because here I'm going to have negative mu Fn equals 1250 A. So we want to solve, we need A. Given the information in the question, how do we find A? Kinematics. What's VI? 65 kilometers per hour. You said 16.65? 16.7? 16.67. Okay. Meters per second. So we took kilometers per hour. We converted that into meters per second. What's VF? 0, because hopefully the car comes to a stop. Actually, we're told it does. What else do we know? Distance is? Distance is 35 meters. So now I've got meters per second. I've got meters. My acceleration is what I need to find here now. So we're going to use VF squared equals VI squared plus 2AD. 0 equals, now we said to the right was positive, so that 16.67 is going to be positive. So we've got 16.67, and we're going to square that bad boy. Plus 2 times A times 35. So A is going to equal negative what? 3 point, so you said 97. Connor, what did you say? Hey, oh, I totally forgot to do that this morning. I'm so sorry. If you snaggle the key from Betty, their box is at like hip height in that secret paper room by the front door. Sounds good. Just email CC Cal and email me. Negative 3 point what? 9797.
I'm getting 96 now.
96 what?
3.96.
Exactly?
No, it's 9841.
So
97.
thank you. Got to round properly, Connor. So now we're going to take this and we're going to shove it in there. So I've got now negative mu Fn is 12,250 equals 1,250 times negative 3.97. Mu then is going to equal, these negatives are going to cancel. Oh, sorry. We'll zoom out a little bit here. 1,250 times 3.97 divided by 12,250. That should be mu. Mu then should be 0.4. That seems reasonable. Because this is going to be almost 10, like dividing by 10. 0.4 seems reasonable. You follow? Where did it get complicated? Or where did it trip you up? Oh, that, oh.
So I just did the 1250 times negative 3.
Oh, okay, so you found F net and you're going to take it one step further.
I found F net first.
Yep.
And then I was going to find coefficient of friction. Then I was got confused and didn't know what to do after.
Right. In this case, it's a little weird because F net is only one force. It's only the force of friction.
Yeah.
So, yeah, no, that makes sense. So that's 7. Anything else? We good with the rest? 8, because are we going to slowly march through all of them? Is that what's happening here? Or because now I've done 6 and now 7. I'm happy to do 8, but am I going to have to do 9, 10, 11, 12, and 13 after this?
Yup.
Okay, cool. 8. I'm happy to do 8. Let's take a look at 8. And then we're moving on, perhaps. Here's the car. A 950 kilogram car, so I've got FG acting down, I've got FN acting up. Constant velocity, and we're told how much force is required by the engine to maintain the speed. So I've got a force forward, and I'm going to have a force backwards. This I'm going to call F engine. This is going to be force of friction. Fg is going to be 950 times 9.8, so Fn is going to be 950 times 9. I'm just going to go here. Let's just give her. So now, because this thing is constant V, A equals 0, therefore F net equals 0, therefore F engine equals force of friction. These have to be balanced. And F engine is what I want, which I'm just going to call F big E. So we are going to have force friction is equal to mu Fn. We know mu. Mu is, where did it go? 0.125. Force of friction is 950 times 9.8, and we're done. Comments, questions, concerns about 8? I feel like the F net piece is what's tripping us up. Is that where we're getting hung up?
Yes.
What do you mean? There is no acceleration. So jumping back then into kinematics. So we need to slow, and this is often where, students start to struggle in physics because we're now pulling things from all over the place. One sec. Hey, Betty, what's up? Yo. Just school clothing is fine. Okay, cool, thank you. Bye. This is where, especially in grade 11, I often see students getting messed up because they're starting to realize that physics is all just word problems. And word problems involve a little bit more than just plugging and chugging. Like, you guys have to slow it down and think through all of your steps, and there are implications every step of the way. And as soon as I ask for more than 2 or 3 implications, math students start to be like, this is never going to end. I don't want to do the things. Every piece, and you just got to, I think you got to force yourself to slow down and reason this through step by step. This whole chapter is always going to start with F net equals ma. It might simplify it by saying constant velocity, which means there is no a, which means we're just balancing forces. But if there is an acceleration, then it's back to here. This guy right here, if I need to rehash, let's rehash. Sum of all forces in the direction of motion. So if this thing's moving left, right, I need all my forces left and right in there. Some are going to be positive, some are going to be negative, because they can't all be positive unless they're all acting in the same direction, and you've called that direction positive. Sometimes this acceleration is going to be given to you. Sometimes this acceleration you're going to have to find given a whole bunch of forces that we know. Sometimes you're going to have to use kinematics. So this is either going to be given. This might be your final answer. Or you have to find using kinematics.
I got screwed up on the plus or minus of that the combination of forces.
Okay. So that's going to come from decide on a positive direction. Something you got to do. So if I flip back to here, that's this stuff. If you want me to go back, I can give you more F net equals ma kinds of practice. But where this stuff comes from is, in this type of problem, you got to decide what direction you want to be positive. If you're acting in that direction, great. Then the sum here is going to include positive values. But any forces that act not in the positive direction are going to show up here as negative values. I think I might do one more to show you what I mean. but I think, is breaking it down like this a little bit helpful?
Yep.
Okay, let's do one more of these things, because we've got the time today to do it. Number 9, why not? Let's do the next one. Okay, so we've got a dragster. There's my dragster. Did we do number 9? No. We did not do number 9. Hands up if you didn't do number 9. Oh, you did not do number 9? All these hands did not do number 9? Fantastic. Do number 9 right now, given what I've just done and what I've tried to talk through here. There is your dragster. I want you all to do number 9. Except Manuel, he can sleep. I want you all to do number 9. Tristan, I want you to do number 9. Get your stuff out. You have nothing out. Where's your stuff? Like at home? Okay, well, I got the scrap paper up here at the front. Harshan's got the question beside him. Share the question. Or you can, just go up to the front and grab, I got extra packages. Go grab another package. There's no excuse to have nothing. I can provide you with things.
down.
That is not even. For number what? What did you divide? For number 9? Yes, what did you divide? Oh, so I think I've got it. I have no clue. Come on. What was the number? 13? How did it get 0.1? Wait. Yo, I got 0.132. I have no clue what I did. You can try and read my work, but I can't even read it. It's the top there. Yeah, we have the same acceleration. So you got me there, yeah. I got this. Yeah, I know. I divided 1848.75 divided by 1.95. I rounded some it exerts 13. So we have acceleration.
Okay, we figured out number 9?
Hold on 1 second.
No, I can't.
Let me put this down.
I got it.
Okay, so let's talk to you about number 9. Where are we hung up on 9? Okay. Do you have questions about 9?
Your advice helped me very much.
Well, the advice is just, I just consolidated everything that I've been doing over the last week to, this is how you must think, which is, what you gotta do.
I don't know why my calculator failed me the first time, but I got it.
So sometimes we call that a Petcak error. Problem between calculator, between share and, actually that should be another C. Between calculator and share. Problem between calculator and share. It's a fancy way of saying it's a user error. Do you ever call IT support and they say, oh, it's probably a Petcak error? They're making fun of you. Pro tip. Okay, so, because the calculator is going to do exactly what you tell it to do every time. So it's not the problem.
First time I type something and I don't know, I write the numbers correctly and for the reason I must have missed the decimal
Probably.
or something stupid and it gave me 1.32, not 1.23. 0.123.
Are there any, are we feeling a little bit better?
Easy.
Okay, let's super duper honesty time here. You know what, I'll even pause the video for super duper honesty time. So that's the end on 9. And then whatever your calculator tells you this is, should be 0.123-ish, depending on how you round it along the way. I mean, you could have multiplied these together. You got a value here, like it's. But.
Okay.
We good, Jimmy? Okay. We're good? Okay. Where was the snag? Here? Like you put the value, like what was?
Yeah, I just got confused, like there's a few blanks. That's why it's probably not.
Okay. Yeah. This is where it gets really important to make sure we've written down like the formulas along the way with the variables in there. But you want the entire piece. Draw the diagram, like just the entire way of thinking through these things is what you want to try and emulate. Okay, so that was friction. Welcome to friction. Now for something entirely different, flip the page. What is it on? Everything that we've done in this chapter? All of it?
So once we finish this,
Yeah.
okay.
Yeah. Okay. Here we go. Elastic forces. I want you to grab a computer. All y'all, grab a machine. Actually, what's the best way to do this? You know what? We're going to forget this one. Flip over here. We're just going to go straight to this because I want you to play with stuff on the other end of things. We'll play with things after, not before. Okay, so we're going to skip that one and we're going to jump straight into it. We're talking about something called Hooke's law. Hooke's law is something that governs elastics. And so often Hooke's law is going to be what we use to find what we call the elastic force. Now, if you had to explain elastic force, how would you explain? We all know what elastics are. You've played with springs before. If you had to explain elastic force, what do you think it is? Luis?
It's like an object had a
form, but you can like pull it off. You try to change the shape of the object, of course. Try to maintain the object at the same stage as the initial one. So, can explain it. Like,
Okay, hold that thought right there. Connor.
Okay. It looks like you're bracing for impact.
No, my eye hurts for some reason. Keep going.
Basically something that stretches and is resisting stretching.
Okay, so Luis gave us a very technical definition. Connor gave us a very simple definition. They are equivalent, and they're both correct. So I love it. So let's use some of the language from both of these guys. The elastic force, governed by something called Hooke's law, is a force that works to return a distorted object back to its, the word I'm going to use here is equilibrium. Back to its equilibrium state. This is also sometimes called its rest state. And lots of things are elastic. Some things are obviously more elastic than other things. Examples of objects that are elastic. Springs. Sure. When you yank on a spring, the spring yanks back on you to a point. Does anyone ever mangle the slinky so that it doesn't slink anymore? Okay, so you can exceed the elasticness of an elastic or a spring, but if you keep them reasonable, like if you treat them nicely, you're going to maintain that kind of springiness. So springs is one example. Give me more examples of things that behave elastically. Yeah, rubber bands, which we're going to play with today. What else? Anything with rubber in the title?
I would say like the money elastics that are used to put money together.
Yeah, we call those rubber bands as well.
Okay.
Yeah. This is another language, another words for that. Tires, sure. Not really. Some of them are so small that we can't talk about them having an elastic force. Like a
a rubber ball.
rubber ball, we like rubber balls. Or like a bouncy ball. I'm gonna call it a bouncy ball. Some things work elastic in one direction but don't work as well elastic the other direction. So for example, if I were to take a cork, you guys know what cork is? Like a wine cork,
Oh yeah, yeah.
but like that material. If you squeeze it down, it will push back against you and bounce back to its original form. But if you take a cork and you rip it apart, it will tear apart pretty easy. It won't like slink back very easy. So some things are elastic in some directions and not others. A slinky, springs, we don't typically push them in because at their rest state, they're fully compressed. We stretch them and then they compress back down. So different objects behave elastically differently. Some resist being pushed in, some resist the pull. All of them want to stay at whatever their equilibrium state is. So we got springs, rubber bands, tires, bouncy balls. There's a few more things typical in everyday life, and sometimes less every day, but we still see them. If I take a whole bunch of springs and I use a mesh fabric to allow these things to be strapped into a circle, I got a trampoline. All of the balls, yes. Basketball, a rugby ball. I'm just going to say basketball, etc. All of the sports balls do this. Hockey sticks are another one. Yes.
Oh, because they
Baseball bats are yet another one. Because to really get them, to get that puck moving, you're not just swinging a stick at a puck, you're leaning into it, creating a whole bunch of flex, and it's that extra, when it deflexes, this happens too. Golf club less, golf ball more. It doesn't bend, a golf club bends a little bit. Not as much as a hockey stick or a baseball bat might. They do? Then I'm not nearly familiar enough with golf. So these are some examples. So here's what Hooke's law is. Hooke's law states that the amount, it's a T, of, yeesh, that's gross. The amount of elastic force is, in the language, I've said it, but we haven't written it, I'm going to use it properly here, is proportional to the amount of distortion. What do you think that means? Connor.
So basically, the amount of elasticity that's available is directly related to the amount of, I can't remember exactly what distortion means, but I think it has something to do with what's being pulled, so the availability of
Kind of. You're trying to say it fancier than perhaps is necessary. Distortion is me pulling or collapsing. Yeah, Cohen.
Power depends on how much it's actually distorting and how much it's bending.
Right. Yes, exactly that. So the amount of elastic force is directly related to how much I'm forcing the spring out of its rest shape. Like if I take a trampoline spring and I pull it just a little bit, the amount of elastic force is going to be pretty small because I haven't done a lot to that spring. But when I actually, how many of you ever built a trampoline? I have more than I expected, which is great. Building a trampoline gets very, very difficult, especially near the end, because you've got heavy springs that you've got to stretch a pretty good distance. So Hooke's law says that the amount of elastic force depends on how much you've distorted this thing. If you give it a large distortion, there's going to be a lot of elastic force pulling back on you. That proportionality means that when we say things are proportional to each other, that means our force elastic is going to be equal to the distortion. And now for the distortion, we use, sometimes it's written as delta x, sometimes it's just written as x. I'm going to leave it just as x here. So when things are proportional to each other, we say that the force elastic is equal to, like directly equal to, what we're going to call the distortion here, up to some multiplier. So like we had it with gravity. We said gravity was proportional to the mass. The more mass we had, the larger the force of gravity. And then we had that multiplier out front, big G, that adjusted it for us. Yes? You remember what I'm talking about? Okay. So with our elastic force, with Hooke's law, we don't have a big G. Force of friction is the same. The multiplier out front was the coefficient of friction, mu. For springs, we have a coefficient, we call it K. So we say that F elastic is equal to K times X. Where X, sometimes it's going to be written as delta X, is the stretch from the rest position. And it's going to be measured in meters because all distances in physics are measured in meters. And K is what we call a spring constant. And everything that is springy will have its own spring constant. And this value K, so like with coefficient of friction, the larger the coefficient, the more friction. Same thing here. The larger the value for K, the stiffer the spring. So K is also a reflection of the stiffness of the spring. And I use that word spring loosely because a hockey stick isn't a spring, but it has springy qualities. So we're going to use this F equals Kx here. So let's do a couple examples, and then we're actually going to get you guys, we're not going to actually bungee the thing. Actually, no, we totally are. We'll see. We're going to do a lab. Here we go. So, a student stretches an elastic band with a spring constant of 50 newtons per meter by 15 centimeters. How much force are they applying? So, we're going to draw this thing out. What's happening here, just so you can understand what the wording in the question actually means. What's happening here is we have an elastic band. There's our generic elastic band. And a student is taking this elastic band, and now, so this is at rest. Now they're stretching it. Okay? And what's happening here is this distance here is the 15 centimeters. So x is, we said it before, x is the, I should zoom out a little bit, the stretch from the rest position. So for a spring, or for an elastic, this is what it was at rest. We don't care how long it was at rest. This is how it's being stretched. The only part of the stretch that we care about is how much longer it was than when it started. So this is the 15 centimeters here, and we want that in meters. So we divide it by 100, and we get 0.15 meters. So now the question is, how much force are they applying? Well, to hold a spring with in this case an elastic with the 15 centimeter extension, it's important to recognize what's actually happening. The F elastic is pulling back.
Can you put it like FE?
Yep. I'm only going to write it F elastic like a couple more times here, just so we get comfortable with it. So you've got F elastic and F applied. The F elastic is the rubber band trying to pull back. The F applied is what the student is actually doing. And in this case, they are equal to each other because it's being held there. So we can then say that the F applied is going to be equal to my F elastic, and we know F elastic is given to us by this expression, Kx. So K is the spring constant, which they give us in the problem. That's the 50 newtons per meter. So 50 times, actually I'll put it in brackets, our extension is 0.15 equals the force that the student is applying. So what is 0.15 times 50? Sorry? 7.5 what? What are the units on that? Newtons, because it's a force. Cool. That's it. Comments, questions, concerns? Let's do a couple more then if there aren't any. Al MacInnis, which is a name that sadly probably doesn't mean anything to any of you, had the hardest slap shot in the league, in the NHL, for a very, very long time. And he used a wooden stick to do this. Wooden sticks are much, much stiffer than... Any hockey players here now? Any hockey players? Okay. Wooden sticks are a lot stiffer than composite sticks, which means if you can bend it, it's going to give you a whole heck of a lot more oomph behind it. And he was a big man, and he was able to lean on these sticks pretty hard, give him a lot of flex, which means when they flung the puck, they flung it real hard. So he used a wooden stick that had a spring constant of 850 newtons per meter. What is the distortion on the stick if he exerts a 525 Newton force while taking a slap shot? So, here's your standard hockey stick. This kind of looks like a scythe. There's your standard hockey stick. When a hockey player, if you've ever seen it in slow motion, which doesn't sound like many of you have, if you've ever watched a hockey game, seen it in slow motion, how a slap shot actually happens. I won't bend this too much because it'll snap it otherwise, but what happens is, like, a hockey player will come up and they'll bring their stick down, and when it hits the ice, it actually gets a lot of bend, where it ends up looking like this. And they do it such that the tip of their stick drags along the surface of the ice, and when it comes in contact with the puck, as they raise the stick, it snaps back. So these guys get these incredible slap shots. So what you have here now is a stick that, instead of looking straight like this, actually ends up looking like this. And the whole thing bends. And what we want to find is, what is this guy right here? What is the bend on the stick, or the distortion on the stick? So, this is just a, sorry?
How fast does it go if it bends 62 centimeters?
Is that what you found? 62 centimeters? Okay, so let's finish this off real quick here then. F elastic equals Kx. So we had 525 equals 850. That's our K value times X. So then you found that the extension was 525 divided by 850. So you said, Manuel, that X is equal to 0.62 meters. So that's 62 centimeters. That's just over 2 feet. So let me show you a picture of Al MacInnis slap shot.
Are we able to calculate the fastest one?
I can tell you what his fastest shot was. That's easy.
But do we have the knowledge to, like,
No, to take this and turn it into the speed at which the puck was moving, there's too much going on there. Slap shot. Okay, so his slap shot is ranked as the hardest ever in NHL history. Goalies regularly declared it to be the scariest shot they faced. Even though it was technically slower than some of the more modern slap shots. So in the early 90s, his slap shot was 96 miles per hour.
what's the baseball pitch? It's like
100 and a good fastball is going to be over 100 miles per hour.
would it be faster, like, before or after it hits the bat?
So you get something that looks like, so here's this. Here, I'll show you this. This is a good example.
So, look at this way. Car on the highway.
Okay, so if this stick were straight, it would come down like this. This isn't, yeah. So what you're looking at is this distance here, this deflection here. So let's see if I can find a better one.
Oh, that's big right there. That's big.
This is a big, slow motion video. Sure, we can look at slow motion slap shot. Why not? Let's go videos. We don't want images. I gotta pause this to say, bat's too thick. It's really not the bat that's flexing. It's the core of the bat. It's the core of the bat that's, like I said. So things are elastic in different directions. A bat actually compresses and then springs back. That's part of what the bat's doing. So that's why having different cores in the bat can be questionable. Also, it gives you more swing speed. But and the ball itself actually has, if you've ever seen the inside of a baseball, there's cork and stuff on the inside of the baseball, and that's what's causing it to spring off the bat as you compress the ball. So let's do one more. This thing is called a redneck slingshot. A 65 kilogram girl sits in a redneck slingshot that has a spring constant of 10.5 newtons per meter. If the sling is stretched by 45 meters, what is her initial acceleration when released? So here's what we've got. The redneck slingshot is on the ground, and we're going to kind of go off on whatever. No, I won't do that. It's staked into the ground and then pulled back. You hold it like the Angry Bird thing. And she's being held here by someone else. And when Buddy lets go, what's going to happen? Now, this stretch is happening. This is the extension right here.
Can you make an Angry Bird question in your next test?
I can try. Okay. So the question is, what is her initial acceleration? Well, if we want initial acceleration, we're going to have to apply what we now are seeing in Hooke's law to F equals ma. So now we've got F net equals ma, and this is the A I want to find. Now, the net force, the force acting on her in the direction of motion is going to be what? The only force that's going to be acting on her in the direction of motion when Buddy lets go is the elastic trying to get back to normal, right? So there's going to be a massive Fe. We think it's going to be massive anyway, that direction. So, I mean, redneck slingshot, this is also like a water balloon slingshot, same idea, but way bigger. What are you doing, Tristan? Well, come back to your desk. Oh, it's easier for you to see? Okay. So then we're going to have Fe equals mass times acceleration, and Fe is going to equal Kx is equal to ma. So we got Kx equals ma. So K is, we're told, is the spring constant, 10.5. X is 45 meters. Her mass is 65 kilograms. What's her acceleration? Initial acceleration. Can someone verify Khalil's answer? 7.26?
If you round it,
If
it's 2.7.
you round it, it's 2.7? So it's 7.26 what?
9.
Okay,
7.27.
7.269. So yeah, 7.27. We got to make sure we round it properly. Yes, good. Meters per second squared. There it is. So a really fun way to turn elastic force into a good time. Well, really bad time when she hits the ground, but yeah. I'll show you another video that would be an interesting problem if you wanted to tackle it. So we're going to do the bungee jump. Now, this is, I went and talked to Mr. Morrison while you guys are working on that first question, and we're running out of weights. Sorry, I shouldn't use that word. We're running out of masses to actually use, so I can't give you masses to do this. So what we're going to do for this first experiment, not even really an experiment, it's kind of an experiment, is you guys are going to figure out the spring constant of an elastic. So I'm going to give you an elastic. You can give this some stretch to these things. They're all same brand. They're all the same thickness. They should all be relatively close to the same length. But your job is going to be to find out what the spring constant of this is. Now, because we're running out of masses, we have lots of really heavy ones, but they're going to cause these things to snap pretty quick. What we're going to do instead of using actual masses is what you're going to use is what's called a spring scale. Now, a spring scale uses, the scale has been pre-converted for you. Typically what a spring scale does is that's going to probably break. Let's get something smaller. I'm going to use this water bottle here for a minute. Excellent. Okay. So what a spring scale does is the conversions are pre-built into the scale, but Manuel, what is the weight of this thing according to the spring scale?
4.5 newtons.
Okay, a little less than 4.5.
Or what?
Yeah, a little less than 4.5 newtons.
Okay.
So we could then convert that into a mass if we wanted to.
What's the time?
Don't worry about the dynes. Dynes are weird. I don't actually know what dyne is, so ignore it. So we can calculate the mass of this by doing what? Taking that force, that 4.5-ish newtons, and doing what to it? Dividing by 9.8. So this goes straight ahead and does the weight. Now, instead of the water bottle, what if I took this thing and pulled on it? I'm exerting newtons, but I could very easily convert the force at which I'm pulling to a mass, yeah? I would just have to say, well, I'm pulling with a force of 4.5 newtons. So if this were a mass hanging in here, what would the mass be? That's effectively what we're going to have to go back and do. It would be 4.5, sorry, 0.45, because I just saw you go to 0.45 kilograms, so 450 grams. So because we're not actually allowed to use the masses because Mr. Morrison is saving them for his IB students, we're just going to use these spring scales. Sorry? Why do they get them?
Yeah.
Because there aren't very many of them, and he's being very protective of his equipment, because this equipment just goes missing. The small masses that won't damage these things are like small-ish, and so they just have walked away over the years, and they're expensive. So we don't get to use them, apparently. So you guys are just going to do basic approximations with pulling things. So what we're going to do is, in partners, we've got this page here. I'm not the purpose. You can write this down. The purpose of this, to find the spring constant of a rubber band. That's what you guys are going to do. I am not going to give you a procedure. You're just going to play within reason. You don't get to go outside. So you can see here, what is the rest length, Naya, of the elastic band? 7 centimeters. So then everything is going to be, that we're going to do here now, is going to be based on that 7 centimeter base length. I shouldn't have to say this, but I'm going to say it anyway. Be careful with the setup, because as soon as I do this, that's not what I'm concerned about. This is what I'm concerned about. You see the problem here, yes? Okay? So be careful what you do with this and how you operate it. Don't do it intentionally, unless the person deserves it. But I will tell you whether or not they deserve it. But what you're doing here is, what we're trying to do here is, you want to make sure that the elastic band is very close to the edge so that we don't get some sort of weird angle changing our length measurement. And you're going to pull down with a spring scale to simulate what it would look like for masses to add to these springs. You're going to do this 1, 2, 3, 4, 5, 6 different times. You're going to have to then convert your, convert the spring scale reading into a mass. Actually, you can use this column here because you're going to be able to see what that is later. Wherever the spring scale says, ignore this, use this. And then the extension isn't going to be the total length. The extension is going to be what?
Total length minus 7.
The total length minus 7. Because 7 was the rest length. We don't care about the rest length. We don't care about the total length. All we care about is the difference between the two. Okay? So that's what we're going to do. You're going to do that for a bunch of these things. Then you're going to graph this. You're going to graph force, and you're going to graph extension. So you're going to get meters. You're going to get newtons over here, and meters over here. You're going to draw a line of best fit, figure out the slope, tell me what the y-intercept should be, and we'll do that. Cool? Love it. On your mark, say give it. You can do this in partners. We got more than enough equipment. for you guys to be partnered for this. Make sure you grab a 20 Newton scale, the beige ones, not the 5 Newton scales, the bluish gray ones. As you're working, if you need a hand, let me know. Real quick, because I want you back here to do this. Not far. You can stay, like, don't go past Crossroads and don't go past the comfy area. You're here. But yes, you can go in the hall if you would like.
Oh, okay, yeah, I wanna hold them. No, don't worry about that. Bro, this is the last thing. It's gonna break out of me.
You want to grab a 20 Newton scale, not a 5 Newton scale. So the other one first. You just need 6 different extensions. You can't max out the spring. So I don't know, maybe go to.
Let's do 40 Newton for the last one.
Eventually you're going to exceed it, you're going to break it, things are going to get weird. So you have to kind of adjust your expectations to match. And if the 20, hey guys, I figured the 20 Newton one would be good. If it's proving to be too much, like if it doesn't give you small enough divisions, then jump back to a 5, see what happens. But no, that's not an extension. That's the total length. That's the extension.
That's not my finger. Hey, can I talk to your dad?
Let's put it there.
So four.
Okay,
Yes.
how are you to do like this more than one time?
Sorry?
How are you to do this like more than one time?
You can't assume that one is going to be sufficient. One measure is never sufficient. I want 6 different ones.
Oh, I keep switching this up.
Because you did it once, you moved down for this measurement. This is my K value. But what happens when things get weird as I stretch this thing through? You want to make sure that it's consistent. So you want to find 6 pairs of extension and required force to make sure that you get a good value for K.
Well, we're going to redo it. Why, look at this, why is there less length? Or more like 3 newtons than 4?
211.
26
Okay, so let's do 3.
Yes, you do. Okay, so in addition, ladies and gentlemen, I want you to finish this. This is something you should be able to do over the weekend. That is the next 4 days, and I want you to do these 4 questions here on spring extension. I'm playing with a lab that I might get us to do an egg bungee off the rotunda. We're looking. If I've got a couple procedures. If I can work it out, we're going to throw eggs off the rotunda, and you guys are going to have to figure out the length of string required to hit a 4 centimeter water pool without damaging your egg. Is going to be the goal. So if I can get the procedure worked out, that's what we're going to do next week. So please make sure you have at the very least made a reasonable attempt at completing this, and definitely do those other 4 questions. And I'm going to try and get you this procedure for the egg bungee. It's going to be good. Comments, questions, concerns? Spring's not super complicated, but you got to be, just thinking it through the same way we've thought through everything else. When the bell goes here in less than a minute, you may also go. I would prefer you not all congregate at the door. Stay like what happened yesterday. Don't do that. Just stay where you are. Stay near to your home in this classroom. And when the bell goes, you may also go.